So this is a major issue. So what is the issue? The issue is the following, right? So then the issue is phi of x in RD may be too hard to compute. When I say hard, not it's perhaps not in the hardness sense, but then the number of features might be prohibitively large that you don't necessarily want to compute phi of x. So the question then is, well, unless I compute phi of x, it doesn't look like I'm going to be able to apply my PCA, right? So I know, of course, I can apply my PCA when D is much large by looking at the matrix phi of x transpose phi of x. But then even if we can't compute phi of x, then does it mean that everything is doomed, or is there a way out? Now here let's notice the fact that the eigen directions that we are going to compute in PCA is only of that of phi of x transpose phi of x. This is the matrix for which we will compute the eigen directions. So essentially what you really need is phi of x transpose phi of x, right? So meaning you need a matrix where you need the pairwise dot product between any two pair of items, right? So if I give you an xi and xj, so what is essentially happening is, if I give you xi and some xj, you are mapping xi to a high dimensional space and you are mapping xj to a higher dimensional space, and then both of these are given as input, and then we are essentially computing phi of xi transpose phi of xj. Now this would be our kij, and we will take the eigen vectors of k, right? So which means we essentially need phi of xi transpose phi of xj, right? So the question is, this is one way to go achieve this, right? So this is the input xi xj, I will map it to phi of xi phi of xj, which I can compute this. Now is there a direct way to go here? Meaning, without going this way, where I compute the phi's first, right? So I apply the phi, explicitly compute phi of xj, and then compute the dot product. Is there a way I can directly compute the dot product? Because that's what I need anyway, right? So I need to know the dot product in the higher dimensional space. So is there a way I can compute this dot product without explicitly computing this phi? So this becomes an important question to ask, because unless we answer this question, we won't be able to really apply PCA to, nonlinear relationships that matter, right? So in the sense that if you really want to capture some high dimensional, some complicated pth power relationship, then you must be able to do this. But how do we do this, right? So is this even possible? This sounds like magic, right? So without computing phi of x, how do I compute phi of xi transpose phi of xj? Is it even possible? Let's ponder about this for a minute. So let's take an example. Okay, so here is an example. Let's say x is f1, f2, and x prime is g1, g2. Okay, and now let's say consider this function. I am just pulling this function out of the hat, but let's say we want you to consider this function for the moment, right? So x transpose x prime plus 1 whole squared. Let's say this is the function that we want to care about, right? So now what is this? This is just f1 f2 into g1 g2 plus 1 whole square. This is the dot product. Now that is f1 g1 plus f2 g2 plus 1 whole square. That is f1 squared g1 squared plus f2 squared g2 squared plus 1 plus 2 f1 g1 f2 g2 plus 2 f1 g1 plus 2 f2 g2. So x is f1 f2, x dash is g1 g2, and x transpose x prime plus 1 squared is this complicated looking thing. Now let's say I collect terms which are dependent on f separately, and I look at them as a vector, they look like f1 squared from here, f2 squared from here, 1, let us say square root of 2 f1 f2, square root of 2, I will tell you why the square root, I am doing it's a square root here, square root of 2 f1 and square root of 2 f2. Let us say this is one vector, and now I am dotting this with another vector which is g1 square, g2 squared, 1, square root of 2 g1 g2, square root of 2 g1, square root of 2 g2. Now, you can see, you can verify that this dot product is exactly the same as x transpose x prime plus 1 squared, where x is f1 f2 and x prime is g1 g2. Now, interestingly, what we have managed to do is that these two vectors are of the same functional form, right. So, with respect to f and g. In other words, so if I give a general f1 and f2, then you take the first component, square it, second component, square it, then put a 1, then put a square root 2 f1 f2 and so on, you get this mapping. If you do the same thing for g1 g2, you get this mapping. So, basically I can think of this as phi of x transpose phi of x prime, where phi of x equals phi of, basically x is some a comma b, some vector a comma b is just the vector a squared b squared 1 square root of 2 ab square root of 2a square root of 2b. Of course, if a and b are f1 and f2, I get this vector. If a and b are g1 and g2, then I get this vector, and then I dot that, I get what I want. So, basically what we are able to do now is, what we have been able to do is the following. So, this function that I have asked you to consider, and this is the main insight, right. So, at least as an example, nevertheless this gives us an insight. Often examples give you most insights. So, x transpose x prime plus 1 squared is an interesting function, because this computes the dot product in a transformed space, right. So, where f1 f2 get mapped to f1 squared, f2 squared, 1 square root of 2, f1 f2, square root of 2 f1, square root of 2 f2, and similarly g1 g2 gets mapped g1 squared, g2 squared, 1 square root of 2 g1 g2, square root of 2 g1, 1 square root of 2 g2, right. So, basically we have mapped x which is in R2 to phi of x which is in R6, right, and then we have managed to compute the dot product in the mapped space without explicitly computing these two guys, right. So, I never had to compute phi of x, right. So, because given x and x prime, I am just doing this calculation. This calculation is x transpose x prime, which is a 2-dimensional vector dot 2-dimensional vector plus 1 whole square, right. So, now that is a low dimensional calculation, but then the number that results can be interpreted as if I did a high dimensional transformation of x and x prime to phi of x and phi of x prime respectively, and then I took a dot product in the high dimensional space. So, essentially we managed to compute phi of x transpose phi of x prime without explicitly computing phi of x, and that is worth stressing. So, let me put that down, right. So, we managed to compute phi of x transpose phi of x prime without explicitly computing phi of x. So, this should give us some hope that we can actually, continue this technique and then try to see if we can solve the PCA problem when you have non-linear relationships among features, right. So, we will do that, but before that, so this is just an example that we took, right. So, where x transpose x prime plus 1 squared is just one example which tries to map a 2-dimensional feature to a 6-dimensional space. But are there other examples, right? So, because we have a technique or a technique to solve, once you have this power to compute dot products in a transform space, it makes sense to look for other examples where you can do this general, right. So, of course, mapping in from 2 to 6 dimension is not that useful. I mean, I might as well do the exact mapping and then compute the covariance matrix and do all sorts of things. But what would be important is if this can be done for a general d-dimensional feature where you need pth power, right. So, can you do that? Is the next question we will ask, and the answer to that interestingly is yes. And we look at some more examples now, more examples. Here is another example, right. So, let us say we have the function, some function k which takes x and x prime, and then it calculates the following x transpose x prime plus 1 power p, right. So, for some p greater than or equal to 1. Now, x can be in general d dimension. Now, the interesting thing is that, and we will not really prove this, but then this can be shown to be a valid map, valid function. What does it mean to say a function is valid for us, right? So, when will we say we are looking at valid functions? Well, for us valid means the following, right. So, that means that there exists some phi, right. So, and this phi typically is from d dimension to some capital D dimension such that if I just compute k of x comma x prime, which is this quantity here, it's same as computing phi of x transpose phi of x prime. It is as if I went to this high dimension using phi and then did a dot product. If such a phi exists for a k that I give you, then well, k is a valid function, because otherwise if this does not happen, I cannot rely on k to compute my capital K and then take its eigenvectors and so on for PCA, right. So, this function here is in fact a valid function, and it's a worthy exercise to argue this, right. So, I will give this as an exercise. Compute the explicit phi for p equals 3 and p equals 4. How does these phis look like, and what happens to their dimension, right. So, I mean, to convince yourself that this is indeed a valid phi, you need to be able to compute this phi, right. So, if you can, I mean, that is one way to convince yourself. If you can exhibit a phi, then that phi that you have exhibited is a certificate of validity for this mapping, right. So, that there is a transformation where this function is exactly computing the dot products. Remember, not all functions are going to compute dot products in some high dimensional space. I mean, I could have given you an arbitrary function, but then if you want to convince yourself, then one way to do that would be to actually exhibit this phi, exact mapping, like how we did for p equals 2 when you had just 2 features, right. So, please do this as an exercise. I mean, this will reveal some insights about how the dimension increases as you increase d and p. Okay, one more example, and this is perhaps another famous mapping that people typically use in machine learning, is the following, right. So, your k of x comma x prime in this case is e power minus x prime squared by 2 sigma squared for some sigma greater than 0. So, this should remind you of Gaussian PDF. In fact, sometimes this is also called the Gaussian map, but the standard term is also called as the radial basis function. This is the radial basis function. Two important points about this, right. So, the first thing is that can be shown that this is also a valid function to be a valid map. Again, valid in the sense that you can exhibit a phi where this is exactly computing the dot products in the higher dimensional space. But what is this higher dimension? That is actually even more interesting. So, interestingly, if you think about this, you might actually be able to kind of see why this makes sense. Phi in this case maps x to an infinite dimensional space, right. So, the higher dimension that we are talking about here is actually infinite dimension, right. So, infinite dimensional space, right. So, earlier we said that the dimension where it gets mapped to increases in certain fashion d to the p and so on. In fact, in this case you can think of, I mean, you can argue that the phi actually maps every data point to an infinite dimensional space, right. So, well, whenever there is infinity involved, there are a lot of technicalities, but you know, technicalities aside, we do not want to you know, dig deeper right now into the technicalities of what does it mean to say space is infinite dimensional and so on. Technicalities aside, what you can do is you know, can think of this as mapping a point, a data point to a function, and I will tell you what this means in a minute, and dot products between functions become integrals. So, because this is an infinite dimensional space, you can think of it as if it is a function, right. So, what is a function? A function is something where you give an input and then out comes an output, and the input can be any real number, whereas it is infinite of them, and then in fact uncountably infinite of them, and then the output is also a real number, let us say. Now, you can think of the whole function itself as an infinite dimensional vector, right. So, where if you kind of I mean loosely treat all the inputs in a vector, then all the outputs also become a huge infinite dimensional vector. Of course, you cannot put down everything, you cannot write down everything if it is uncountably infinite, and that is why we should think of this mapping itself as mapping a point to a function, right. But that is just technicality. Now, how do you do dot products after you map points to functions? Well, because this is infinite dimensional, your dot products is essentially a sum, but instead of sum, in the continuous case it becomes integrals, right. So, that is what you do to exhibit that this is in fact, I mean, a valid map. Another way to think of why this should be a valid map is to see that your e power x itself can be written as a power series expansion, where you have kind of all polynomial powers, right. So, of course, with decreasing contributions, nevertheless you have all powers embedded into e power x itself. So, in some sense you can think of it as you know, mapping it to an infinite dimensional space where you have all powers contributing in different ways, right. So, that is one way to think about this as well. Yeah. So, what we have done now is we have kind of given you multiple examples, right. It's a host family of examples, polynomial maps, and then there is this radial basis map and so on. But in general, can we give all these valid maps a name? Yes, sure, we should give these valid maps a name because they will become useful. And the name that is used is what is called as kernels, right. So, this is a kernel function. Kernel is a multiple, I mean it has multiple meanings in mathematics, but for our purposes in machine learning, we are going to think of kernel functions as functions which are valid in the way that we described earlier. That is, they compute dot products in some higher dimensional space. So, we write this as follows: any function, again loosely writing these definitions, given a function k which takes two d-dimensional input and then outputs a number, any function such function which is a valid map, right. So, I am not defining valid again, that is what we did earlier. It means that there exists a phi such that this has this dot product interpretation is called a kernel function. Okay, so what is k of x? If k of x comma x prime happen to be x transpose x prime plus 1 power p, which is what we saw earlier. So, this is called as a polynomial kernel with power p. So, if k of x comma x prime is e power minus x prime squared by 2 sigma squared, now this is called as a radial basis, or sometimes it is also called as a Gaussian kernel, right. So, now these are specific examples, but I think the more pertinent question is, I mean, it is not necessary that these are the only kernels which are useful or relevant for our problem, right. So, maybe there are different nonlinear combinations which might help us. So, in general, we want to ask the question, given a function, right. So, let us say I give you a function k which takes in 2 d-dimensional vectors as input and then computes a number. Now, how can we say it is a valid kernel, right. So, if I give you a function and I ask you, well, hey, I claim that this is a valid kernel, now how would you be convinced that this is in fact a valid kernel? Well, we have seen one method already to convince ourselves so that is method 1, which is the standard method, where you are going to say that, hey, you think this is a kernel, well, which means there must be some mapping phi, right. So, if I can exhibit such a mapping, a map phi explicitly, like how we did for the quadratic kernel, right. So, the power 2 kernel, we exhibited that phi of x explicitly and said that x transpose x plus 1 power 2 squared is actually a dot product if you think of it as this map, right. So, in the mapped space. So, that is one way to argue this, right. So, but sometimes this might be hard, right. So, might be hard sometimes to come up with this explicit mapping, might be harder or rather hard sometimes. So, if this is not always possible, is there an alternate way we can convince ourselves that a given function is kernel? Because not all functions are kernels, right. So, is there a different way to argue this? Yes, there is, and this is given by what is called as the Mercer's theorem. We will not delve deep into this theorem in this course, but then I will at least give you a informal version of this theorem, right. So that we get the essential understanding of this theorem. I will not state it in full rigorous mathematical detail, but then we will give enough mathematics so that we know in practice what it means, right. K, which is RT cross RD to R, I am given a function k and then I am asked if this is a valid kernel function. Is a valid kernel, Mercer's theorem says it is a valid kernel if and only if, which is a very powerful theorem, right. So, that is why it is a powerful theorem, because it characterizes validity of a kernel if and only if two things happen. A, k is symmetric. What does that mean? That means that k of x comma x prime should be same as k of x prime comma x, that is this. Now, why should a kernel be symmetric? Well, we know that the kernel is going to compute dot products in some high dimensional space, which means k of x comma x prime has to be phi of x transpose phi of x prime for some phi. Now, because dot product is a symmetric operation, so k of x comma x prime should also be same as phi of x prime transpose phi of x, but then phi of x prime transpose phi of x equals k of x prime comma x. So, it necessarily has to be symmetric, right. So, if it is not symmetric, if I give you a function which is not symmetric, In other words, if you can find x and x prime where k of x comma x prime is not same as k of x prime comma x, then you can immediately dismiss my claim that k is a kernel. But let us say if it is a symmetric function, then that does not immediately mean it is a kernel already. You will have to check one more condition, and that condition is the following. Again, I will write this in a machine learning way of looking at things, but there is a formal way to state this as well, which I am not doing, right. So, for any data set, let us say you consider some data set which has n points. There is no restriction on what this data set should be, because we could have gotten any data set. The matrix K, which is an n cross n matrix, where you have Kij equals xi transpose xj, that is, sorry, not xi transpose xj, I am sorry about that. So, Kij is the kernels evaluated at xi comma xj, right. So, I give you a data set, you are trying to claim if a k is valid kernel or not. Now, construct a capital K matrix where capital Kij is the kernel evaluated at xi comma xj, right. So, now of course, this is a symmetric matrix because k itself is a symmetric. We have already, let us say, verified k is symmetric. But can we say more about this matrix? Well, the Mercer's theorem says that this matrix is positive semi-definite. Well, what does that mean? That means that all the eigenvalues, right. So, this just means that all eigenvalues of k are non-negative, right. So, so if I give you a data set, I mean, you can pick any data set, construct the capital K matrix as Kij equals the kernel evaluated at xi comma xj. So, that would be a symmetric matrix because kernel is a symmetric function. And now you compute the eigenvalues of this matrix, and the claim is that all the eigenvalues have to be non-negative, right. So, well, Mercer's theorem says that these two conditions are not only necessary, but they are also sufficient. It is slightly involved to argue the sufficiency side, but at least the necessity side it is easier to argue, and we will do that in a minute. For instance, we already argued why k should be symmetric, right. So, it is necessary for k should be symmetric because dot product is a symmetric operation. Now, can we argue the necessity for the eigenvalues of capital K to be non-negative? Well, we can do that because if, I mean, we need k to be of the form Kij to be of the form phi of xi transpose phi of xj, right. So, which means k should be phi of capital X transpose phi of capital X for some matrix or some phi, right. So, we do not know what the phi is, but then there is a phi. Now, if you look at the eigenvalues of this phi, we know that they would be same, at least the non-zero eigenvalues of phi of x transpose phi of x, right. So, phi of x transpose phi of x, the non-zero eigenvalues of this is same as the non-zero eigenvalues of phi of x into phi of x transpose. But then this is just a covariance matrix or the scaled covariance matrix in the higher dimensional space. And we know that the scaled covariance matrix has the property that, you know, all eigenvalues are non-negative, right. So, simply because they compute you know, the eigenvalues equal to the variance in a corresponding eigenvector's direction, and variance is a positive quantity, right. So, and so the eigenvalues of phi of x transpose phi of x should also be non-negative, which means that if k is a valid kernel, then the capital K matrix should have necessarily non-negative eigenvalues. It could be 0, but then it has to be non-negative. Now, this is an argument for necessity, right. So, both A and B are necessary conditions for K to be a valid kernel, but Mercer's theorem says that these are enough, right. So, these are also sufficient for K to be a valid kernel, right. So, we will not prove Mercer's theorem, but then that is important to know.